Start section 6.1, chapter 6, Algebra 2, evaluating the nth roots and using rational exponents. Nth roots. So we've been dealing with square roots a lot when we were talking about quadratics, or maybe we introduced a couple cube roots. So nth root just simply means some root, power 2, power 3, index 2, index 3, index 4. So in this setup right here where we have this radical and then this little n out in front of the radical and then an a underneath the radical, this is called the index. And this is called the radicand. And the symbol we talk about when we take roots is the radical. So we're going to see how this relates to some of our exponential properties that we looked at in chapter 5. So rational exponents. What's a rational number? So a rational number is the quotient of two integers. Something like that, where b can't be equal to 0, obviously. So we're going to have fractional exponents that we're going to be dealing with, and we're going to learn how those fractional exponents relate to the concept of an nth root. All right, so a couple key concepts: the real nth roots of some radical or radicand value of a. So we're going to let some n be some integer greater than 1 here. A is a real number. When our a is taking an nth root such that the n is an even integer, here are the circumstances here are the results that we get. Can't take a square root, for example, of a number that's less than 0 or a negative number. So we, in that case, get I values or no real roots. If we wanted to take the fourth root of 0, or any root really of 0, fourth being even, fifth being odd, you'll notice that these two are the same, odd values of n versus n being an even number. We get 0 for that circumstance. We've been dealing with square roots before. We know that when we take square roots of a positive number, we get this plus minus the nth root of a, or plus minus a to the 1 over n power. And this is the relationship we're going to look at, this radical form to exponential form. We're going to look at that today. Odd integers. Well, we can take the third root of a negative 8 and get a negative 2. So when the a value is negative or positive, you still get real solutions, which is different from our even. But we've actually already messed around with that stuff a little bit. This is just a formal discussion on that. All right, let's just get right to the problems here. Just working some simple stuff to understand the concepts of this nth root, and we'll take a look at how the calculator can be used. And we're going to have portions of this exam that will be non-calculator, and it would be related to these kind of problems here that we see in the first two examples. All right, finding the real nth root now, given the following. So we're following this format. We're talking about nth root of some value of a. And in this case, I've got the fifth root of a negative 32. So what that's wanting me to find is there is some number that when I raise it to the fifth power that gives me a negative 32. So I've got an odd n. That means it doesn't matter if I get a negative in here for my nth root. So I'm thinking about, okay, what number times itself 5 times makes negative 32? Well, we know that 2 to the fifth gives me positive 32, so that means negative 2 to the fifth would produce negative 32. So the answer to this is negative 2. Odd n value. What about an even n value here? So we have now the sixth root of some value of 1, and an even, make sure we remember that this is what we're looking for, some number raised to the 6th power equals 1. So an even, remember, gives me plus minus solutions. And in this case, plus minus 1. Negative 1 to the 6th power, negative 1 times itself 6 times, produces 1. Positive 1 times itself 6 times, produces 1. So that's a fairly straightforward one. Whenever your radicand is just a 1, your answer is going to be a 1. The third root of a negative 64, we're back to an odd. So what is it that raises to the 3rd power that produces a negative 64? Well, a negative 4 times negative 4 times negative 4. And you can check these on your calculator. You can check with, there's usually a function on your calculator, a key that looks something like that. And then above it might be something that looks like that. And those are the keys that allow you to do different roots besides your generic square root button, because most calculators have their own square root button. This one is allowing you to find nth roots of some value. And how you input the numbers into your calculator is dependent on the calculator itself, so you might want to read your manual on your calculator how to do that. But calculators do have the ability to do this, so you might want to check it out, make sure you understand how that works with your given calculator. What about rational exponents, and how does that help us relate to a radical? So there are some formulas, some things we need to definitely know if I'm going to put my flashcards together, or if I'm going to do my write in the back page of my notebook, some things I definitely need to know. They would be these two things. I'm going to add one little piece to this. So now we have some number raised to a fractional exponent, and that fractional exponent in turn becomes a radical value. Now, in this example, a to the m over n power, we see it written this way. There is another way that we can express this. So in this example here, we're taking the root first, and then we're raising to the power of m. We could also raise to the power of m first, and then take a root. So you could see it written like that, where the power is on the inside of the radical for the second example, and on the first example it's on the outside. So when I have fractional exponents, what I need to know is that the top number is a power number, and the bottom number is a root number. If I can remember that, it helps me in when I set up my radical form. Okay, and then this one's just saying, again, dealing with our negative exponents, let's make them positive first. Let's stick those negative exponents down in the denominator if they start as negative in the numerator, or if they started negative in the denominator, we'd move them up into the numerator to make them positive. So you would make that change first, and then you would apply these properties. So, for example, 125 to the 2/3 power, this is the same thing. I have two choices here. I could either do 125, the cube root of that, and then square it, or you could do 125 squared and then take the cube root of that number. Well, one of those is much easier for me to do without a calculator, and it would be this one. Because hopefully you know that the 125 is a perfect cube, and that means I get a 5 in there, and then I square it, and I get 25. Or if I try to do 125 squared, well, then I'm going to have to do longhand multiplication, 125 times 125, and then have to break that down into perfect cube radicals. So it might take me a little longer to get to that point. What about b? There's a couple different approaches we could do with b. One of them might be, let's make that a positive exponent first. So now I have 1 over 8 to the 4/3. And then this could be cube root of 8 to the power of 4. It could be 8 to the 4th power, cube root of that. The way that I've got it written here, though, is I think a little easier to work with. So cube root of 8 is a 2. raised to the 4th power gives me a 16. Now another way you could have looked at this problem, somebody might have seen the problem this way. They looked at this, they saw a cube root of an 8, and then they had a power of a -4. Well, that means I've got a 2 to the power of -4, and that means make it a positive, and I get back to the same place. All right. What about just doing some approximation work here? Taking some calculator time here, just to make sure we understand how our calculator works. 22 to the 1/4 power. Again, once you know how your calculator functions, another way to raise to a power on your calculator is most calculators, not all of them, have this, we call it the caret key. And that's how you can raise something to the power of either a fraction or another number. So if I'm going to put this in my calculator, I'm going to do 22, and then I'll hit that caret button. And then if I want to actually physically put in a fractional exponent as a power, I want to use a parenthesis and go 1 divide 4, close the parenthesis, and then that will tell me my answer. So if I did this, 22 to the 1/4 power, I get 2.1657, and we're going to just approximate it to 2 decimal places. So 2.17 approximately. If I did that with 35 to the 5/6 power, I would get 35 to the power of 5 divided by 6, and I get 19.35 approximately. So you do have to remember, if you're going to do this in the calculator, that you do include these parentheses here. Otherwise, your calculator is going to go 22 to the 1st power, get that number, and then divide by 4. So just be careful if you're putting this in the calculator to check. Solving. So we've been solving all along, and what we do when we solve is no different. We always try and isolate what we have as a variable so that we can get it by itself. Well, isolate means to get it by itself, and then therefore come up with a solution. And in the process of isolating, sometimes we add, subtract things to the other side of the equal sign, and then we multiply or divide things to the other side of the equal sign. That's no different here. The only difference is now we have some powers that we're working with. So we're trying to get not just x, but let's get x cubed by itself, and then we're going to undo these powers by using radicals. Or we could even use fractional exponents. All right, so in this case, I'm going to divide by a 6, and I get an x cubed is equal to a 64. All right, if we use radicals, you undo a power with the same radical. So if I want to do a cube root and get rid of it, I have to do, or sorry, if I have a cubic power of 3 and I want to get rid of it, I have to use a cube root. So once the radical index number and power on the inside, once they match, then just the radicand comes out. And then cube root of 64 I know is 4. Now another way you could have looked at this, thinking about fractional exponents, is if we always try and make our powers 1, x to the first just gives us x. So I could do this too. I could raise to a fractional power, the reciprocal here. That gives me 3 times 1 over 3. I'm using my exponential properties right now. Power of a power property. So 3 times 1/3 is just x to the first. And then I have 64 to the 1/3 power, which is the cube root of 64, which is giving me that 4. So there will be times when it is advantageous for us to be thinking about using a fractional exponent versus a root when we get into some more complicated simplifying problems. X minus 8 quantity to the 5th power. So here we've isolated already our exponent, which is good. We're ready to undo that power of 5. So I'm going to take a 5th root and a 5th root, and I get an x minus an 8. And if we left our answer in radical form, the 5th root of 100, there are no factors of 100 that are perfect fifths. So perfect fifths are 1 to the 5th, which is 1, 2 to the 5th, 32, 3 to the 5th, 243. None of those are factors of 100, so I could simplify radically the 5th root of 100. I'd leave it alone. And then I could just add the 8 over there. And I could have that answer. Just looks a little funny. We're not used to seeing it that way. Or you could convert the 5th root of 100 is 2.5 roughly. So again, I'm going to go practice putting the stuff in the calculator here. We're going to do the 5th root of 100. And we get 2.5118. So approximately 2.51. And this becomes 10.51. And again, that's an approximate value. It's not exact. This would be an exact answer. Not real useful for me in terms of like calculations wise, but like if I was talking, maybe I was solving for x equaling time or something. It would be better to leave our answer as a decimal for time than the 8 plus 5th root of 100. All right, then we have this last one here. So I get rid of the 2 to isolate. 729. So now I got an even root. I'm undoing by taking a 6th root. That automatically gives me 2 answers. And in this case, 729 just happens to be a perfect 6th. So I get plus or minus 3. All right. Now let's get to some application of where we're going to find this radical stuff and fractional exponents. You're going to find in our application problems and in some, well, there are things that you are expected to know, and if you don't know them, you got to be creative about going about finding the answer. So one of the things here we're going to have to think about, I can't really do anything with this problem. So I've got water in its liquid state has a density of 0.9971 grams per cubic centimeter. Ice has a density of 0.9168 grams per cubic centimeter. And a cubic container is filled with 600 grams of water, liquid, and another one is filled with 600 grams of ice, solid. Round the answers to 2 decimal places when appropriate. All right, so the first thing we got to do, if I'm going to work on anything with this problem, is understand the concept of density. Density measures mass per a unit volume. And generally speaking, we use little d. So I really kind of need to know this before I can go anywhere with this problem. And then I got density as a mass per a unit volume. So now that I have that out of the way, maybe we can go and take a look at the volume of the container filled with liquid here. I have, and this is, we're looking for water for this one, so I'm looking at the density of water is equal to the mass of the water divided by the volume of the container. And notice that this question is asking you to find volume. I need to find that. And I need that V value. I don't want it in the denominator. It's not by itself. It's not isolated. I want to get that V by itself. So maybe before we start plugging numbers into anything here, we first manipulate the equation to get V out of the denominator. And how we would do that, one way we can do that is to multiply everything by V. Then it becomes V times the density of water is now equal to the mass of the water. And then simply divide by density of water, and we have volume. So volume is equal to mass of water divided by density of water. And that's the equation we're going to use here. So volume is equal to, the mass of our water, it told us, was 600 grams. And the density of our water, it said, was 0.9971 grams per cubic centimeter. So we had grams on top. We had grams per cubic centimeter here. And so when these things manipulate, multiplied by the reciprocal of grams per cubic centimeters, grams cancel and we end up with just centimeter cubed. And this answer is, I believe, 601 point something. 601.75. We're going to round it to 2 decimal places, is what it told us to do there. So 601.75 grams, cubic centimeters. There's our volume. That's the volume of the box we would need to fill this water. All right, now that we know that, let's build the box. So it told us that it's a cubic container. And a cubic container means that all the sides are the same length. And for the sake of what we're doing here, we're going to just use W to represent the width. Normally, we know that the volume of a rectangular prism, which is what we have, is width times length times height. But if all of those are the same units, we just call them W, then we know that volume is equal to W cubed. All right, so finding the length of the edges of this container. Well, volume, W cubed. Trying to find W, which means really we just need to know what the volume number is. And that's what we found up on the problem above. 601.75 is equal to W cubed. So now we apply our properties here. How do we undo that cube? We take a cube root. And we get that the width can be equal to, take the cube root of that number. And we get 8.44 centimeters. So an 8.44 by 8.44 by 8.44 centimeter box would contain all of this water. What about if it was in solid state? How about ice? What's our volume here for ice? Ice density is a little less than our water density. So we still have our equation that we used up above, that the volume can be found by mass over density. So we have this time the mass of ice over the density of ice. 600 grams of ice, and our density was 0.9168. And this will give me my volume for my ice. .45 cubic centimeters. So we see that this is significantly more, and it's because my density was smaller for ice than it was for the water. And so my box is going to have to be bigger dimension-wise. So if my volume is still for a cubic container W cubed, but now my volume is 654.45. I have to cube root both of these, and I'll get my container bigger than the last one. .68 centimeters, slightly larger. And there's your size of your side on the cubic container. So there we see some application. Hope that was helpful.